Hi everyone. So we are going to start the event right now. And first of all, I would like to welcome all of you for the Keras Community of Sri Lanka. This is the first time we are having this event in person. And yeah, so to start off the session, in the first lineup we have the session on the introductory session on Keras, which is done by Mr. Taraka Devinda, who is a consultant at Dialogue Asiata. So I would like to invite Tarak Devendra to take the stage and to start the session. Thank you.
Testing 1, 2. Yeah. Testing done. Training. Okay. Good morning to everyone. So, as an introductory session, so I think there might be people who are familiar with Keras, have been using Keras for a long time, and there might be people who haven't used Keras. So I decided I'll do a session sort of like a quick start. So in every like library or whatever we use, we don't usually go to the documentation and read them when we encounter them. What we do is we go to the quick start and then we start looking at what's there and start doing it. So this is something like that. I'll show you what's inside Keras and how things are done in there. By the way, does any one of you know what Keras means? Why do they name it Keras? Nobody knows. So I won't waste a lot of time. So it means a doe made of horn. Horn means horns out of bulls and these animals. So in the story, the Trojan war story, there is a dream. There's a place that dreams come through. Two doors. One door is made of one door is a white door that dreams come and they don't get realized. Keras is the door that dreams come and get realized. So they named it after that because this is a library that you can realize your dreams in your machine learning or in your artificial neural networks. So what's Keras? So Keras is a so I can't see my own slides. Okay, wait. Small session, so you'll know some of the things that's inside Keras once we are done. So we've all seen a neural network. So in a neural network, what we do here is we think of it as in layers. So in each of one of these, we have an input layer, we have a set of hidden layers, and there is this output layer. So in Keras, what we do is we build this network with layers. So to do this, we have the layers package in Keras. So depending on what type of neural network you're building, we use a specific type of layer. So if you are using a typical neural network fully connected layer, you define it as a dense layer. So this is how in the first code snippet we define it as dense. So in layers dense, the number 10 means how many neurons are there in this particular layer. So you can fully connect 10 neurons to the next layer. And if you are likewise, if you are doing image recognition or convolution, you have a convolution layer which has 10 activations, 10 layers, and then you can define the activation function likewise. So if you want to do a 3D convolution, there's a separate class called con3D. You can use that. So likewise, there's a lot of type of layers. So the concept here is we think of layers rather than individual neurons. And then inputs and outputs. So whenever we use a neural network, we have an input, we have an output. So in order to define what the input is and how it is sent, how data is sent to the network, we use an input layer. So when defining the input layer, we define a shape. So the 10 comma here means we give it inputs of 10 dimensions with batches. So whatever there is, there are 10 types of inputs with batches. And then depending on the output, we define what the output layer is. So the output layer is also a typical layer that we defined before. So in softmax, if you have, let's say for in this particular situation, you have 4 layers, you have 4 neurons, and the activation is softmax. You have a probability that you're getting, that is the value is, the total of the value is equal to 1. If you're classifying, let's say, cats, dogs, elephants, and parrots, you input the image, and depending on which image the network is seeing, the higher there will be a higher probability in that particular neuron for the image that you're seeing. And if you're doing a regression, you might want to do a single neuron where the value actually means the output value you want to see. Yeah. So we know how to how individual layers are constructed. So how do you create the entire model out of these layers? So what we do is we connect these layers together to make the neural network model. So in Keras, there are 3 ways you can do this. One is the sequential API. The next is a functional API, and then you can subclass the model class in the Keras package itself, and then do if you want more advanced type of model creation. So I will show you sequential and functional. So in my experience, I have never wanted to like go as deep as subclass in the model. So I've done sequential and functional. So sequential is fairly simple. It's exactly what you have seen in that image. So you have an input layer, a hidden layer, and then an output layer. So this is a very simple sequential neural network. So here we define the output shape as 2 inputs, input shape as 2 inputs. So we have, let's say, something like 2 values of some data set, and then we have a fully connected layer which consists of 3 neurons next, and then we are doing a classification of 4 classes, which is a softmax activation. So here we have an input, output, and a hidden layer in the middle. So this is how you define a sequential model. So when you use sequential, the name sequential means every time when a sequential method is used, the neural network needs to be from the start to the end, it needs to be like a sequence. So one after the other. So there is no branching, or there are no multiple paths that your data can traverse. So that is not possible with sequential. So to overcome that, we have the functional API. So when you're using functional API, you can do things like branching. So there might be 2 different input layers. There might be 3 different outputs, things like that. So in this particular example, I have shown here is there are I don't know whether you can see it, on the very top there are 2 inputs. On the right hand side there's another input. So there are 3 inputs in this particular network, and then you branch it in, and then you come to 2 different output layers. One of them is a classification of 4 neurons, and the other is a value that you give to so let's say something like a confidence value, things like that. So if you want to build a neural network like this, the functional API is where you have to look for. So how do you build the functional API? So here we have an example. So in inputs, you create the input layer. So here we have a layer with 784 input neurons, and then next we create another layer, a dense layer with 64 neurons, and when you want to connect them together, you use the second layer as if it's a function in Python, and then pass the input layer as a parameter. So X is the next output. So when you give the dense layer, when you call the dense and inputs, there is another X that comes out, that is the output. So if you want to plug in another layer after that, you have to use the next layer, define another layer like say dense 1, and then call X from that dense 1 layer. So likewise, you can build neural networks that are not sequential but branches off in different locations and then combines and gives you customized network architectures. So there's a very good possibility that you might be using this in your RL lab in the evening. So this is how you do it. So this is the basics of how you do it. And then we come to pre-processing. So whenever we read data, we don't get it in the format that we want to get it. So this is where pre-processing comes in. So sometimes what we do is we pre-process the data itself using another script or using another Jupyter notebook or whatever that means that that's available to us. But when it comes to putting this model into production, that might be a problem. Let's say you have a data set of let's say cats and dogs, and you prepare a model that you could classify between cats and dogs. You get images of different sizes, different image depths, and let's say like whether they are color or they could be black and white. So what you do is you bring them into a certain dimension, a certain type of image, so that you can put it inside the network. So you would create a unified input layer, and then you would prepare your data that suits that input layer. So if you create a Jupyter notebook and do this, of course you can do it, and then you can train the model and then go forward with it. But the problem arises when you are deploying this. So let's say if you deploy this on a let's say on a mobile phone. So who's going to do that pre-processing for you? Nobody's going to do that. So whenever you receive an image, whenever a user clicks an image of a cat or whatever the user clicks on, you will have to do that transformation on a different platform there in that case. So in order to reduce that, in order to eliminate that issue, what we do is we have pre-processing layers in Keras that you could snap on to the neural network in front. So whenever you do this with the neural network itself, what we can do is we can test and train our network with the pre-processing layers intact, and we can do our model evaluation and testing all that with the pre-processing inside the network itself. And when we deploy our network, we can deploy the same network, then we can put it in production, and we won't have any problem because we have that pre-processing in the model itself. So I have two examples here. One is the normalization. So if your data comes in, you want to normalize it, you put a normalization layer in front. If you want to do things like image resizing, image rotations, cropping, there are things like that, pre-processing layers like that. So odds are you might be using a separate script to do this on the first start. But the recommendation is when you reach a certain level, you put these layers onto the model itself and then proceed, because it's very easy to deploy. Then we come to compiling the model and fitting it. So when you want to after you build this model, you would want to train it. So before training, you would want to compile the model. So when compiling the model, we have to give three important parameters. One is the optimizer. So which kind of optimizer are we using for this particular model? So there are a lot of optimizers in Keras. So you might want to check them out in the documentation itself. And then how do you calculate the loss? So the loss could be something that that's in Keras. There are a myriad of loss functions. So you could name it in the compile statement, use the class itself, or you can use a different placeholder here for loss, like a string placeholder, that would also work. And then during training, what metrics do you want to see out of this model? So you can, let's say like RMS error or something like, let's say any parameter inside the model, you would define here. So during training, you would see all those parameters when you give the list of parameters here in the compile stage. So in the example here, I don't know whether you can see it here. So in here we have two metrics. One is the binary accuracy and how many false negatives are there. So whenever you're training the model, in every step you would see these parameters. And then after compiling the model, you would fit the model. So similar to all the ML libraries and all the machine learning that we do, fit means you train the model to your data. So what do you send the model here? X and Y parameters. So X is our data, Y are our labels, and then you have to specify the batch size of the inputs. Let's say how many in what size of batches that you're sending it. Let's say 100 or 200, 64, things like that. So then how many epochs do you want to run this model for? And then the callbacks. What kind of callbacks do you want out of this model? So callback event happens. So let's say if you're training the model, you reach a certain accuracy, you don't want to proceed beyond that. Let's say you reach 90% accuracy, you don't want to change the model after that. That's what you want. So then you would use a callback and say this is where I want to stop. So you would want to put a early stoppage callback there, so that it would stop there rather than changing the model and risking reducing the accuracy by seeing the data afterwards. Or you could do things like error calculations or there are a whole set of callbacks that you could do during the training of the model. And then we come to inference. So after we train the model, you would want to call the model and then get outputs out of it. So when you want to let's say get predictions out of it, we call model.predict to do that prediction. So whenever we call our model.predict, this X would be whatever we would give it as the input. So this is where I said if you have things like pre-processing, this is where it comes in. So it's really important that we could give whatever we have at our hand without pre-processing them. So after you train the model, you can save the model into a file, reload it in a different environment and do predictions, and you can load it in any environment like mobile environments or JS front ends. So yeah, that's what I have for now. So if you have any questions regarding the process, I can answer. So I hope you, like the people who are really new to Keras, I hope you guys got some kind of idea what you're going to do. I think the next speaker would go for a hands-on here, so you could feel the real flow here. If you don't have any questions, I will end. Okay, thank you very much.
Thank you for that session, Taraka. So to give you the token of appreciation, I would like to invite Chamoche Hanka. Right. So the next session is on to take over the stage. Control P.
Okay, so good morning everyone. I'm Tim Nirmal, and in this session what I'm hoping to do is hand-on experience on using machine learning with Keras. So before moving forward, let me introduce myself. So I'm an undergraduate of Faculty of Engineering, University of Sri Jayawardenepura, and I'm a machine learning intern at LSEG, and also I'm a ML and AI enthusiast. Also, you can contact me and with me these social media handles, which goes by Timir Nirmal and Tim Nirmal. So, who's this session is for? So, I'm targeting this for someone who is new to machine learning or Keras. So, I think there are at least few of you among here. So, after this session, I hope you will get a good idea and start on these things. So, in our session, these are the key takeaways. So, first I am going to introduce you to the Google Code Lab, and then some machine learning concepts, and to build some models. So first, what is Google Colab? So Google Developers Code Lab. So Google Developers Code Lab is a set of tutorials and guided hand-on coding experiences that provided by Google, and this include a wide range of tutorials on different topics, products, and some Google events. This is what you can see. So you can choose from different topics and from different products that Google have. And for the today's session, I'm going to follow up this code lab, which is say hello to hello world of machine learning. So when it comes to code lab, you can see a set of steps that you can follow, and you can see the prerequisites and things you need to know before the following code lab. And for the easiness of presenting, I actually added these things to my presentation. So everything in here is in the presentation, so I'm going to follow that. To enter the to explain the machine learning, so first we need to define a scenario, which is activity recognition system for fitness tracking. In here, what happening is we take some inputs from a person, and based on that we define a set of activities that person is doing. So in this case, as inputs we get the person's speed, and as the activity we get like walking and running. So for that, for the first case, let's consider the situation where a person is walking. So in walking, let's say we have condition that speed is less than 4. So we can define that programmatically like this: if speed is less than 4, then status is working. Then if we go to another condition where the person is running, we can define if person is not working, then he is running. We can further extend this scenario by introducing another case, which is biking. So if the person is not working or not running, then the person is biking. So in these things we can clearly make a connection between speed and the activity person is doing. So what happens if we come to a case like golfing? So in golfing, can you define set of rules? No, because it is actually a combination of linear and rotational movements. So it is methods that we can define rules, and that is where the machine learning come to action. So before going forward with that, let's see what is machine learning. So this is actually the description I got from ChatGPT, and I highlighted the special things you need to focus when you define machine learning. So machine learning is a field of artificial intelligence, and machine learning models learn and improve their performance on the task they are specifying by the analyzing data we give it. So based on the things it learned, he can predict the patterns and the experience by the provided information. So we can simply note that thing by graph like this. So for the machine learning model, we give our data and we give the set of answers that matches with the data, and we generate the rules we need. So if we consider the earlier example, the data is the speed and the answers which are the outcomes, whether the person is working, running or something like that, and by that we can generate the rules we need. And the thing we did with the first three scenario, which is working, running and biking, it happens like we define our rules. So that is what we actually do in traditional programming. So we give rules and we give data. From those we expect some answers from the coding. Okay. So with that knowledge, let's move on to create our first machine learning model. And before moving forward, I like to note you to remember that the x in this data table, the x component we call sometimes that features, and sometimes we call it as attributes, and along with that in machine learning we call the y component, which is the outcome or target or result, something like that. And to build our machine learning model, first we need to get an understanding about our data. So can you find a relationship in data this given? So in here we can see that x data points are moving, increasing by 1, and y is increasing by 3. So we can build a pattern that y equals 3x plus or minus something. Next step is to find that something. For that we can use x equals c Keras model and since our data has one attribute per item, we take the input size as 1. So actually this layer corresponding to this equation, which is y equals wx plus b, and after defining our model, next we need to compile it. So for that we need to define the optimizer and loss function along with that. So next let's see how the actually machine learning model is doing its training. So once we define our model, which is y equals wx plus b in this situation, it first assigns some guess numbers for the variables we are using. So let's say first we define y equals mx plus 10. Then with the loss function we can measure the guess answer against the known answers. So we can create a function which include the difference or losses between the actual and the guesses answer. So we use this loss function with the optimizer to make another guess. So let's say it has y equals 5x plus b. So it is some kind of progress because our equation is y equals 3x plus 1. So this happened in few iterations or maybe more, and each iteration it happens we call it as a epoch. So in a epoch a data set is entirely moving through the model for the number of epochs, and to train the model we use the fit function. And next is demo time. And so in our code lab we are right here now. We compiled it and at the training phase. So I added them to a Google Colab and we can run this. So you can see that the loss we defined. So for each iteration it gives the loss. Just sorry, my bad, I didn't share that. Okay, so this is the collab I was talking about, and I run it all, and with that we can see for each iteration we get a loss. So and we can see that it converges towards 0, and right about at the end of the epochs it got a really low loss value, so which is good progress. And we can predict for unseen data with using our model. And for our model we have, if we give 10, it have given 31, which is exactly what we need, because our equation is y equals 3x plus 1. And so this is what we learned so far. This is how we define model, compile them and fit them. So let's learn the things we already learned in little deeper way. So I think in early session these things kind of mentioned, so I'm not gonna stick to them pretty much, but this is the basic machine learning process. This can be extended to few other features like deployment, or there can be iterative movements, but this is pretty much the basic things we have. So first, to train a machine learning model, we need a data set, and then we need to train it. After that, we need to evaluate it, and later we have to test or predict the model we prepared. And also we can perform hyperparameter tunings to improve the model accuracy. So for the preparing data, these are the basic steps we follow. So we collect data and clean and pre-process them. Also there's something called exponential data analysis and feature engineering, which is generating new features from the existing features. And there's data augmentation also, which is generating new data. And also we can take this data set from the TensorFlow, because it has a good set of data sets which we can directly download with a code like this, and it has different splits, trains, test data splits. So yeah, this is so basically in a data set we define 3 sub data set from the data set, which are training data sets, test data sets, and the validation data set. So sometimes test data set and validation data set can be the same. And also after we define our data set, we need to, if we like performing classification problem, we need to separate them into features and labels, and again split them into train and test set. This can be different from the data as the data set you use. And to define the model, there is main 2 ways that we can define model, which is functional API and another one is sequential API. So functional API is actually something more flexible, and we can build complex architectures with this, and which have multiple inputs, output, and we can share layers, branch them. And I think this is already discussed in earlier sessions, so I'm not going to stick to that much. And so this is how we actually define it. It has input layers, then the hidden layers in here, and the output layer. And finally we can conclude it to a model with you introducing the input layer to here and the output layer to here. Also in here, once we define a layer, we need to pass the connection of this layer to here to the next layer like this, and this from this and this from this, so it builds the connection between them. And sequential API is a much simplest way to build layers, because it's kind of stacking the layers one after another. And the thing in here is it only can have exactly one input and one output layer. And this is how we can define a sequential layer. So this is actually the this model converted to sequential one. So we have our input layer here and the 2 hidden layers and the output layer. Then we have to define the optimizers. So optimizers is actually responsive for updating the weights of a network, and by those we can minimize the loss function. So I will explain these things much deeper later, and Adam and SGD are some optimizers we use in Keras. And for the Lex function, it measures how well a model is it measures how well the actual values compares with the predicted ones. And for categorical tasks, we can use the sparse categorical cross entropy and binary cross entropy, and for multi-class classification you can use categorical cross entropy. In normally regression task you can use mean squared error. And there's another thing called metrics which can give to compilers. The metrics task is to monitor the performance of the model during training, but this doesn't participate in any kind of evaluation. So normally in classification we use accuracy, and for regression we use mean squared error. So for the training we use the fit function. So in there are few parameters we can pass. So we should pass the input data set, output data set, number of times the data set should flow through the model, and if we created the validation data set we can pass that. Other than that, it has a shuffling option, and I think the callbacks are also discussed in earlier session. So with those, with model checkpoint we can actually access the model during training and some other things. And for the evaluation we can just simply call the model.evaluation, and for the prediction we can just call .predict function. And when it comes to hyperparameters optimization, it is what it do is there are things in the model that are not learned during the training process. So we call these as hyperparameters, and what we can do is we can either create a parameter grid or something like that, and improve these parameters in this step. So in next and these are the codes you saw in here, and so I think you all are aware of Collab. So from there we can load our data and separate them, splitting, and also in Collab we can actually analyze our data. Yeah. So with this we can like analyze the values, their distributions, like that things, and this is the model I defined for this. And also we can tag the fit function with some variables. So with that we can get the training accuracy and loss of the model. So in next, let's deep dive more into the things we talked earlier. So this is what actually we built earlier, the one layer, one neuron model, and in here we can input the values to that, and these are the weights I talk about. So for the values given here, we define some numerical number and then we multiplied them together, and later we join them together with like this. And also the B part, which is bias, is something that we add after joining these things. And yeah, and with using these neurons, we can define a deep neural network. So it can have multiple layers, like the which one we saw earlier. So we have our input layer and some few hidden layers, and we can have an output layer. So these things are the one actually in one node. And after we develop this network, we need to define the activation function for that, because without the activation function, model is just behave like a linear model, because it just have predefined connections like this, and we don't have any conditions to randomize them. So to make the deep learning neural network more optimum, we need to make them non-linear. In order to do that, we introduce the activation function to the this neuron we made. So what basically happened in there is, it take this sum of these values and then send that value through some function. So these are set of functions that we use. So in Keras you can find this out, the sigma into 1, relo and tan h and everything here. So what it do is, it apply this the sum of the value to the equation, and so we can have some randomness in here. So next thing is gradient descent. So in earlier we talked about the optimizer and the loss, and gradient descent is really good optimization algorithm we use. So what happened in here is, in earlier we said that in optimizer we change the value of the weight and biases based on the loss function. So in here this is our loss function, and we can define change our weights based on that. So what happen here is, once we are in some place, it calculate the gradient or the slope of this curve, and then it move to the opposite direction of this gradient. And in most of the times what happen is, the movement is we can reduce the amount that the weight is going down. So that way we can come to a place where the weight is fully optimized. So our goal is to come this port. And in the loss function, we also have something called global minimum and local minimum. So what happen here is we can have different kind of lower levels. The best one is the global minimum. And with that, I conclude my session. So thank you everyone for listening with me.
Mấy cái bọn nói không? Phải mandare.
Thank you for that session, Timira. So to give away the token of appreciation, I would like to welcome Kushan Bharati to hand over the token. So next up, we have an interesting session on Keras. It's actually on building some visualizing images. So it's done by Keshan Sodimana, one of the former GDG organizers and who's associate architect at LSCG. And I would like to welcome Keshan Sodimana to take on the stage. And yeah.
All right. Hello. Hello. Nidhi? Hello. Right. So, well, it's okay. So, well, it's been quite a while now. I've done a speech at a physical event. So the last time when I did a physical event like this, our constitution had just 19 amendments, and our president was sleeping at 10 p.m. So it was a long time back, and that was a good time, right? Those are the good days. Today we are going to talk about Keras. Of course, it's a Keras day, right? And there's something called stable diffusion. Have you seen something called mid-journey? There was a thing, right? You guys know it, right? Okay. So stable diffusion is something similar, but it's an open source kind of a model. So today we are going to talk a bit about this stable diffusion thing. What you can do with stable diffusion is that you can give a text and it will generate an image for you based on the text. And similarly, you can condition it not just with the text but also with an image. So you can give an image and also a text, and you can do some manipulation, and you can design now like new images, some beautiful creative images. It's like magic, right? If you have seen it, it feels like magic. So today we are going to see what this magic is. Can you guess how many lines of code does it take to run a stable diffusion model? Just a guess, random guess. 100? 1000? 436? Wow. How many? Okay, let's see with Keras. First, you need to install the package, which is a Keras CV. And then you need to do some imports. Actually, you don't need the third line. It is just to show you that the latest Keras core has this new feature where you can use different backends like JAX, TensorFlow, or Torch. Torch means PyTorch. Since we are talking more about Keras and TensorFlow, I was using JAX, which is also a library, open source library built by Google. Yes, I like PyTorch, but since it's a Keras, I'm not going to say I like PyTorch. And then this is all you need. This is all you need. Actually, that's a common phrase that used in Transformer world. Like Transformers means not the movie, but the Transformers architecture world. Because the first paper which came with the Transformer architecture was called "Attention is all you need." So whenever you talk about Transformers, it came to my mind like I don't know how. Now, that's all. That's all for today. This is it, right? Stable diffusion, just 5 lines of code, done. Well, I know that it's a Saturday afternoon, and you came here not just to see me showing like 4 lines of code, which you can easily find on internet, right? You want to see something more. So that's why I'm going to introduce you to an onion. Why onion? Because whenever I think about a new concept, I think it in terms of an onion. So onion is the one first thing that comes to my mind. Because I like to learn a concept layer by layer. So you peel a layer by layer. And the best thing is like when you're peeling the layer by layer, and you start crying, just like an onion. So that's why I like onion when it comes to, when I want to learn something new, a new concept. So let's dive deeper. Let's first look at the different components of this stable diffusion model. So as you saw that, as you have seen, there are 2 components. One is the text. So you are inputting a text to the model, and then it will generate an image. So which means there are 2 main components. You can see 2 major components. One is the text understander. So the model should be able to learn or understand the text that we are giving it. And then the image part, image generator. So based on the text, it needs to generate an image. So basically this is the first layer that we can see. Okay, so let's dive into that image generator part, because we are talking about images here. What is this diffusion thing? Where did it come from? So if you have any previous background about physics, probably you have heard about diffusion models in physics. And the maths behind diffusion models, even in deep learning, has a lot of similarities with the diffusion models used in physics. So to understand it, it's something like this. What is this? So imagine that you are dropping an ink, like drop of ink into water. After a few times, it like dissolves in the water and evenly dissolves, right? You won't able to see like different concentrations on different areas. So that's basically like kind of an idea about diffusion. So similarly, So similarly, you can do something called forward diffusion. So forward diffusion means you have an image, you add some noise, some random noise, step by step. So first you add some small set of random noise to the image. It's like a filter, you know. You're using Instagram filters, right? Okay. So you are adding that filter to this cat. You don't add random noise filters, right? Do you add in your Instagram profiles? But here we are going to add some random noise first, and likewise we are gradually, like iteratively, add more and more noise until we find an image where we cannot say whether this is a cat or not, cat or noise. So the last image, so first image is the original image, and the last image is the image that with all noise. You won't be able to say that this is a cat. This is an image of a cat, right? If you can, just raise your hand. I want to ask you some questions. And then there's another. This forward diffusion is not really interesting because it's pretty common and you can. It's nothing special. But if you can do the other way around, like the reverse diffusion, if you can reverse this process, right? It's a brilliant idea, right? If you can reverse it, it's like reversing the entropy of time, something like that. It's really interesting. So how can we do this? Reverse diffusion is interesting. As an idea, it's marvelous. But the million-dollar question is, how on earth are we going to do this? Because you have a image with lots of noise, and now I am saying that you can reverse it into a beautiful image. Okay, so that's where neural networks comes in. How? There's a model called unit. Actually, in this case, we are using a model called unit, but it's up to you. There could be other models that you could potentially use, and you can do research on what are the other possible models that you can use here. But right now, this is the most common model that used for this particular task. What it does is, it tries to predict the noise, amount of noise that in the image, right? So let's say there's a noisy image, and if you know what are the noise, what is the noise that's in this image, and if you can subtract it, then you have the original image, right? You get the idea, right? You have the noise, image, original image plus noise, and if you can find, predict the noise, amount of noise, and then if you can subtract it, then you have the original image. So that's the idea behind it. It's easy, it's beautiful in theory, but when you're doing it, those are the obstacles that you find. Now, how are we going to train this noise predictor? This is called the noise predictor, and how are we going to train this noise predictor? Now, when you are training a neural network or a machine learning model in general, I think in the previous talk, he was talking about how to train a model, right? So I'm pretty sure you have the basic idea about how to train a neural network or any machine learning model. Now, you need a data set, right? Do you? You need a data set, right? Am I correct? Okay. So how can we can somebody answer me? Otherwise, I'll start sleeping here because nobody's giving any attention. So how are we going to create a data set for this? Any suggestions? Any guesses? Any guesses? How to create a data set for this? So our problem is we have an image with noise, and we need to predict like what is the amount of noise in that particular picture. So what are the data we need to create a model for that? Please, yeah. Image. Noises. Okay, yeah. So what you can do is, you can get a data set with images, good images. Let's say some number of images. Let's say number of images, and you programmatically add some noise, and you have this. I mean, since you have added the noise, you know what is the noise that you added. So there's an image with original image plus the noise, and also the noise, right? So you have you have a data sample with two things. One is the image with the noise and also the noise. So you can create a data set like that. If you have had let's say 100,000 images, you can create a data set of 100,000, something like that. And then this model will, since you have the that training data and the label data, you can train this unit model with that data set. So why it's called a unit is because this architecture actually shaped like a U, like architecturally, because it's you have some layers sequentially, and there are some connections between different other layers. So it's shaped like a U. That's why it's called unit. Now, when it comes to machine learning things, like basically what I would like to say is like just learn the foundation, the fundamental stuff. How to train a basic model. What is a layer? What is a loss function? What is an optimizer? Like all this basic stuff. If you are good with this basic stuff, learning new things is not going to be hard. Like all the complex models will be built upon this foundation. Of course, when it comes to like different models, like the complexity is different, but the foundation is same. If you know the foundation, it's easy for you to learn from forward from there. And also, based on your interest, like different people may have different interests. If you want to just apply, maybe if you just want to do some application level stuff and learn how these different optimizers, different loss functions, different things works. Or maybe you can dive more deeper and see how to implement these things from scratch and learn the maths behind it. So it depends on what you are interested in and what is your goal or what is your real aspiration is. Now, little detour, but let's get back to this again. Now, this unit model, once we trained it, we know that we have a model which can predict the noise. So given an image with noise, it can predict the noise. Right. Now let's do the reverse diffusion thing. As we said earlier, now this model can predict the noise, and we can do the denoising. Like now we can subtract that noise from the original image. So it's not just one step. You can do it for multiple steps, right? So usually it's done for like 20 or 50 steps. You may see it when you are writing the code. You may see that a number of I think I can show it maybe later. So basically what you need to this noise removal part is not just one step. It happens multiple times, and based on this number, the quality of your image may differ. Sometimes more doesn't mean it's a good, because it may have again like removed some more important stuff as well, right? So less or more, it's hard to say like a definite number. It might, you may need to play around with it and see what is the suitable step size that you need to use for that particular thing. But there's a problem. There's a huge problem with that mechanism. What is that? We were working on in the image space. We were working on an image, right? So let's say an image is a 512 by 512 image. There are lots of lots of processing power needs to do this process. So it's not practically feasible. Even for a bigger company, it's not practically feasible for to train such a model and do the stable diffusion in this image space. So how can we solve this? I mean, how can we means how this stable diffusion model has solved it. So basically what it does is it operates in a different dimension, I mean different, we call it a latent space. So latent space is nothing but, how to explain it. So let's think you are kind of compressing the information into a smaller dimensions maybe, like all the information will be compressed into a small area. Like for example, if it's a 512 by 512 image, you may be condensed it to a 4 by 64 by 64, something like that, like a different dimensional, but like in terms of number of computations it's smaller, right? So why it's possible? Because if you take most of the things in the world has a defined shape, like defined properties. If you take a human for an example, if you get photos of all the 8 billion people in the world, there are some properties that's really common for these humans, right? Maybe eyes, nose, mouth, the shapes are like pretty much similar. So what this does is, this in this latent space, all these common features will be condensed, like it can be understood in a smaller region of, actually it's a mathematical space. So so that's why it works in the latent space or a low dimensional space. Now why it works? Because now you don't need to do calculations or do processing on 512 by 512 or a huge number of parameters or huge lots of computers. You don't need to do lots of computation. You can simply work on a smaller scale. So it's pretty efficient, less computation. So you can practically do the application that we were initially talking about. Now how can we condense, or how can we make these images into this latent space? So there's a model called, does anybody know what this model is? There's an encoder and a decoder. What it does is, given an image or whatever, a data sample, you are going to recreate it. So what this does is, so in this particular example, there's a cat and the encoder will encode, or in this case, it's not a real word, but just get an intuition, just think that it's compress it to a particular thing, this latent space. It's a compression, it's not the correct word, but just for the simplicity, for the argument, just think it's a compression, right? The image will be compressed, and the decoder, what the decoder do is, it will again decode, it's the same word, decompress. Like since we compress it in the earlier stage, we don't call it compression and decompression, we call it encoding and decoding. But just for the simplicity, just to get an idea, you first compress it and then decompress into the same image. So if you have the ML background, probably you may understand how to train this kind of an image. So input is this, output is this. So just guess how to train such a model, like what kind of data you need. You don't need lot. If you have the same image, like if you have an image data set, let's say you have images of cats, like 100,000 of cat images, and that's all you need. Again, all you need. Why I'm coming to this statement every time, right? Okay. So what you do is, like, you give the image, and then you ask to predict an image from this model, and you are comparing it with the same image, because we are going to recreate it, right? So you have the original image, you ask it to encode it and decode and predict something. So you get the prediction, and you simply compare with the same original image, right? How close are they? And then based on that, you are going to optimize the model into a certain way that to get the closeness more similar. To make it more similar, right? Now, once you do that, you can simply create images like this, from noise to a beautiful image. Now I know how possible is this. Like I was going through a unit and various autoencoder, and now I'm showing this. Like, I'm pretty sure that you guys are like, what the hell is this guy talking about? I didn't get it. Okay, let's go through it again in a later stage. Now, the second part is that now just assume that you understood the image generation part. Okay, assumption. And the other main component is the text part, right? You had given a text. Now, still we haven't conditioned. We haven't conditioned. Means we are just creating some random samples, random numbers, random noise, and then these images may be random, something random that came from the data set. But how can we condition it for a text or an image that we already have? So that's the thing that we are going to talk next. Now, I was talking about latent space. So how can we manipulate this latent space into a particular way that we can get something we want out of the decoder? Now, for that we need a text model, a model which could understand text and then generate some set of numbers. Numbers means which can be used in the latent space, because I was, as I said, like these models are operating in a kind of a mathematical space. So all the things are like vectors. Those are the things that the models can understand. It doesn't understand numbers. It doesn't understand images. It doesn't understand text. It just understands numbers. It can do only a couple of things. It can do multiplication. It can do additions. It can do subtractions. So those are the basic things that neural network can do. So everything that we have, we need to convert it to something that it can use. So even a text, we have to convert it to some numbers which it can identify. So in the first phase, we are using something called tokenizers. So if you have heard of large language models, this tokenization has, maybe you have heard it. Like, for example, if you are using OpenAI's ChatGPT, even it prices as like for the number of tokens that you are using, or the number of words. So even in OpenAI case, like they said, like 1000 tokens are equal to 750. Like it's an average number. It could vary, but usually they said like 1000 tokens means 750 words. It's an average. Again, it's not really 1000 words are equal to 750, but it's an average. So what this tokenizer does is, given a text, first it map it to some numbers. Like for example, if say I was going home, so I have the word I has a number, say let's say 0, then am will be 1, something like that. So it will map. But the tokenizers that we are using right now are the most advanced one. They are not simply mapping one words into one particular token, because one thing is it has to like the English vocabulary can have millions of words, right? You can even create new words. So how can a text model can be flexible to like understand all these new words? So for that case, a particular tokenizer has a set of like limited number of tokens. Like for example, if you take things like Llama or even Falcon kind of a model, it has like Falcon model has 65k tokens in its model. And what it does is, like if say for example it has a word like, for example there's a word called dream booth, and in the tokenizers it hasn't seen the dream booth word, so it's not a word in the tokenizer. What it does is it can split the word into two. Like dream has, in its vocabulary, dream has, there's a word called dream, and also booth. So it will split this one word into two words, and it will be there will be two tokens. So for that particular word, there will be two tokens. Just an example. So that's how the tokenizers are working. And in this case, usually in stable diffusion models, people are using CLIP model. CLIP is again a model developed by OpenAI, but you can use different other models as well. Now once it does the tokenizer, So tokenization has no meaning, like it's just a mapping kind of thing. So you have to get the embedding. So embeddings means, let's say for example, there are words like, how to say without being politically incorrect. It's hard. Anyway, okay, I'm politically not correct, but let's say for example man, boy, so those are like pretty common words, right? So in embedding space, all the embedding space is politically incorrect, they will be coming to the same region, right? So that's why sometimes the embedding models have, I mean people have done some research on this, especially on the model bias assumptions, how bias are like for example when you say engineer, for example, like whether the model is biased to the masculine or the feminine kind of things. I'm not going to that area now, but yeah, the embedding is something like that. So the common or the most like meaningfully similar things will be clustered in a similar region. So like even a man or boy, like it will be in a same kind of a region. So when you are working with, when you are trying to manipulate it with text, you know, the embeddings that you get will be simply can simply be transformed into a way that the image model can understand. Right. Then this transformed this test will then be going to the noise predictor. Now the overall idea that we were talking about, first you have the text encoder. The text encoder will encode kind of a representation, and then RNG means random number generator. So random number could be 69 lakhs or something like that. Yeah, it's a random number. Like you are subtracting the noise. You are not doing it once, but you will do it for multiple times. So that's the loop that you see here. So the encoded text and the noise patch will go to the diffusion model, and you loop it to maybe 50 times, and then decoder will generate a new image. So that is basically the basic functionality of this stable diffusion model. Okay, now I'm pretty sure you were, I think some of you may not have got the idea properly, so let's go the entire process one more time. So first, a random tensor controlled by seed. So seed is pretty important. It's important means like it's a number that you give for the random number generator to generate something that you can reproduce. Let's say if you have as a seed you have a particular number. Guess a number, give me a number. For my always comes 69 lakhs, but I don't know why. It's a random number, I mean. It's a random number. Why are you laughing? Like 69 lakhs is a random number, right? 69 lakhs is good. Okay. So if you give this random number as a seed, it will create something that you can reproduce. Like if you give 1, then next time again if you give the number 1 as a seed, you can reproduce the same result. Now this random tensor, along with the text prompt, we are giving to the noise predictor. Right? The noise predictor is a unit model that we trained earlier with the noisy image and the noise that we had, right? Can you remember? So that unit model was the noise predictor, and we are asking it to predict the amount of noise in that particular image, and then we subtract it from the noise image. So the unit predicts some noise, and we are subtracting it from the noise image. So we are doing this for not for once but multiple times. So this process will happen multiple times, and once it's done, you are giving that particular whatever this latent variables to the decoder, and the decoder can create a new image. So that's how it happens. and the result will look something like this. So basically initially it's nothing but some random noise, and then it will simply step by step it will become an image which is pretty good. Now this generative images learns latent manifold. What is that? So I'm not going into the details here, but again, like I was mentioning, like these things will learn something pretty intermediary. Like they are not they are kind of abstract, but which we cannot understand. We may not be able to easily comprehend, but they are in a very high dimensional. I mean, in terms of dimension, it's low dimensions, but in a different space, like different mathematical space, which we are not working here, like not a 512 by 512 image kind of space, but it's totally the compression, the encoded, the compressed version of these images. So when you are working on this domain, like usually, as I said earlier, like similar images will be clustered into similar regions. Similar things will cluster into similar areas. Like for example, you can see some animals here. Like birds will come to clustered into a similar region, and maybe the cars or buses or vehicles will cluster into a similar region. So one interesting thing is, like if we have a representation like this, what if we can walk around these manifolds? If we do some interpolation in this latent space, like for example, like this, if you are going from one chair to the other chair, since mathematics, if you although you don't have the images in your training data set, but when you are interpolating, the decoder must decode something similar, right? Because that's the representation it has learned. So a smaller difference doesn't mean you already had the data in your data set, but it can reproduce. It can decode. It can produce something which is similar to these two. So let's say that image and this image. So this is kind of a morphing that happens. You can morph it from here to here, because similar images will be in a similar area, right? Now, I know it's easy for you to understand if I show you this. So now, why are you laughing? What's funny? Nothing funny, right? Did you change anything? No? You didn't change anything, right? People are laughing, I don't know. So here I'm encoding this particular text, and yeah. So I was trying to walk around this particular manifold and see what this has learned. But unfortunately, I believe there were not much data with this thing, so unlucky. So the result was not that good. But then I tried Sigiri. Okay, so this is again the code. Like before going to Sigiri, let's see. So the number of steps here is the number of steps that you need to do the denoising, the loop that I talked earlier. So now 25 times I'm going to remove the noise from the image which is predicted. Now, is it loading? Anyway, there was an image. Yeah, it's not loading, unfortunately. So I created with Sigiri, and again it was not. Yeah, it's not loading here for some reason. But you can try. Like you can try this code. Maybe I can share a notebook with you after the event. So the one thing that you can do if you feel that you don't have enough data for a particular thing, like for example for Sigiri there were not. I guess it's because there were not much of data. So you can, like it's not included here, but you can do some research on how to train a control net. Control net means given a particular image, you can, let's say for example, yeah, let's say again, you need to put CV ray into some heavenly some place, okay? But if the model is not giving good results, you can train a different model called control net, where you like, okay, forget CV ray. Let's say you want to put your face in Mars or somewhere. I don't know. Like it's up to you to fantasize what you need, and you can train the model with your face, maybe 5 or 6 images of your face, and then you can do whatever manipulations around this image. I think there were even apps which are doing this right now. So which is called control net, which is easy to train and it can be easily done in even a free collab as well. So yes, I think that's all I have. Oh, it's loading, right? Okay, finally. No, it's not looping again. I'll say. Okay, it's fine. So you saw it once, right? It's fine. That's all. Okay, that's all. No questions? So 2 things, either you have understood it properly, which I believe yes. Other second thing is again the first thing. Okay, no questions. Cool. Thanks. Have a great day.
Next up, we have Isala Pierisi, who's a software engineer at WSO2. He will be conducting a interactive session. Isala, the stage is yours.
네, 고민 고민.
Hello, check.
screen or full screen? Okay, Suresh. Okay. Yeah, so I'm a bit sick, but hope you guys don't mind. So, okay. If you have known me before, you may think I am mostly known as a Kubernetes guy. So basically, my friends call me Docker Isala. But in here, I'm giving the presentation on Keras, because I think since around 2015 or so, I have been a machine learning enjoyer. So these are the few of the projects I have done over the past few years. That robot is my very first machine learning based project, and the network kind of the thing is my final year project, and this is my SDGP. So all these projects were built using Keras. So in this session, I will be actually talking about how to use Keras to supercharge LLMs, basically ChatGPT. So what the hell is an LLM? So LLM is a fancy term we now use for large language models like ChatGPT or Llama by Meta, and these models are actually based on a model architecture called transformers that was introduced by Google back in 2017, as I remember. I think it's 2017, it doesn't have the date. So how these transformers work is by when we provide it some sort of input sentence, it try to create an internal representation of itself, the sentence itself, to extract the meaning behind it, and from that meaning, based on the thing the transform is trained for example, this transform is I think trained for the translation. It will try to map the given input to the output, basically transform the given input to the output. So, and what ChatGPT also does is they take some sort of any input and translate it to another English output. And so what makes ChatGPT special is basically they have done this with a large data set that is around, I think for GPT-3 it's around 500 gigabyte, and if you give enough compute power for input, compute power and data, it will make any transform, not any transformer, obviously OpenAI had their own magic on top of it, but it will try to do the task it was trained on, basically chat. So now let's see what transformers are actually in behind the scenes. So transformers, this is the paper that was introduced by Google, which specify how this model architecture works. So with this paper, they introduced 3 key innovations. So the first one is this positional encoding. That is where it make the network learn how the sentence is structured. For example, I drove a car or car drove me doesn't mean the same. But for RNNs, for RMN based language models back in the day, main issue it had was they were having a hard time figuring out the difference between these two, even though the words are the same, sentence is different. So to address that, they introduce a technique called positional encoding, which embed the positional, like the positions of the words within the training data itself. And after that, they came up with another solution for this forgetting thing in neural network called attention, which basically make the network learn the grammar and basic grammar and synonyms and tenses from the training data itself, because it's, as I saw, like it first try to learn the meaning and then learn the meaning from the input sequence and then try to reconstruct the output. So and yeah, so for example, another issue this self-attention mechanism try to solve is we can in English, like there are same words that mean different things depending on the context. For example, let's say book, we can say a reading book, or we can say, we also call book as an appointment, we are doing booking. And even for a bat, like so there is a bat for the like cricket bat, and there's an animal also called bat. So the network, when we are training using a transformer, it try to understand the meaning depending on the context. So it can look at a large text and understand what it really means. So this is the actual driving force behind all these large language models that are popping up. So I think you guys are still here with me, and I know this is kind of, even though it seems a bit hard at first, at the end, like within the network itself, the theory is kind of simple. So if you want to like more deep dive, check this video by Google Cloud. It do a great job explaining. So next up, even though ChatGPT does amazing things, it has two critical faults. First thing is the training data for this model is cut off by, I think 2020, I think August or something. So if we ask anything after that, it doesn't have any idea about it. And even though it doesn't have any idea, it try to make things up. So we call this hallucination in large language models. So that's the main problem we are trying to solve today. So to do that, there is a clever technique we can use called, we can include semantic search to upgrade our questions that are sent to ChatGPT. So for example, let's say if you want to know about the latest iPhone 15, so if we ask ChatGPT what is the chip in iPhone 15 Pro is, it will say it doesn't have any idea about it. But with semantic search, what we can do is we can go to Google and query all the relevant data about iPhone 15 and create a database index out of it. We call a vector database, and from that we can use the question and get the most relevant results for that query, and then along with the question we can send that context as well to the ChatGPT, and it will extract the correct information from it. So that's what we are going to do today. So for do that, we'll another check how this that semantic search works first. So semantic search works by exploring a concept called embedding. So I think in the last session also you guys saw what embedding does and latent space, how the latent space works. So I will just brush through it again. So basically this is an autoencoder. So this is not what we are using in the transformers, but this will help you to understand the embedding. So if we look at this image, so the goal given for this network is to reconstruct 4 from 4. But the problem with this particular thing is we have a bottleneck in the middle. So network has to, given image, network has to find a way to reconstruct the same image with very low amount of information, because the encoder and decoder are 2 different networks, so that is linked by the bottleneck. So encoder has to extract all the key meaning of this number 4 and send it to the bottleneck, and bottleneck will send it to the decoder, and decoder has to go through this compressed representation of the image that was given and send it back to user, decode it and send it back. So when we are doing this, the main thing that bottleneck does is it try to capture the actual important data about the number 4. So we can use this same technique to capture data about text data. So like for LLMs, we can, when we train them, we can, it will also build a internal representation of words in the word like this. So for example, so this is actually done for this is presented in 3D form, so we can easily understand it, but in reality these networks go for around 2000 dimensions or something. So when we given like all the given words in the so if we give a word, it will map this within this latent space within the network, and we can use this data given by the network to identify the semantic meaning. So to give an example, you can see here we have king and man, and these are actual vectors in a 3-dimensional plane. So if we calculate if we get the position for this vector king and subtract man from these 2 vectors, we will get queen. So that's how the semantic embedding works. So, and we can use these data that is learned by the network to extract similar things from text. So we'll do a demo on this and see how it's actually work. Yeah, so this is wait, let me okay, anyway, so we'll just I will just Google and go there. Keras. So for this I will be using the Keras example even here. So I have developed a notebook that is loosely based on this tutorial that was given in the Keras documentation. So I will just go through what it is and we'll see the output of it basically. So what this does is it create hope you guys can see it. So okay, let me scroll down a bit. Yeah, so in this code what we are going to do is there is a pre-trained transformer called Robota that was basically trained to do multiple of things, and what we are going to do is take that transformer and create a new extend that transformer and create a new model that basically let us extract those embeddings I was talking about. Basically we can then extract semantic meaning from a given sentence. So to do that we will first get the Keras Robota base model and do few modifications, especially this normalization step where we will get all the output from the Robota network and compress into a single representation. This is, I can, as I remember, yeah, 768 dimensions. So like for the given example before, it was around, I think, yeah, this is 3D, but when we actually go for networks like this, it will go to like these kind of dimensions. So yeah, and for this network we will give a output function to take two sentences and create the cosine similarity as we discussed. Wait, I didn't explain the cosine similarity, I think. Yeah, so okay, so wait. What cosine similarity does is when we given two vectors that are taken from the network that has the like semantic meaning embedded in it, we can using cosine similarity we can find out how close those two vectors are. So for example, if we give yeah, so for example, if we give these kind of two sentences, a little girl is sitting on Santa's lap and a little girl is, wait, that's the same thing. A young girl is sitting on Santa's lap and a little girl is sitting on Santa's lap. We can calculate these two sentences are about 92% close. So with this information we can use this to query any data set we have to find similar things. Let me show you an example for that. So in here I have asked ChatGPT to explain there's a question. Yeah, so I have a question. I'm asking a question called what chip does iPhone 15 Pro has? So if I ask ChatGPT as it is, it will say as of now he has no idea what the 15 Pro has, because like its knowledge is cut off by on 2021. So but in reality this data is available in the internet. So what we can do is we can write a small web scraper function that goes to a like a link that contains information about iPhone 15 Pro, and then we can use that same network we trained above that can extract semantic meaning and put it into a basically here I'm simulating a database. We can put it into a vector database, and after we set it in a vector database, we can query that data by the question. So what this does is go through all the vectors in the embedding database we have created and calculate the cosine similarity. So it will go through all the text we have put in the in this case an array, and calculate what are the closest text that contain when we have that context. And yeah, so these are the contexts it found. Like if you see, like it's kind of hard for us to understand what it says because it's kind of scrambled all across. But because these networks are trained to learn patterns and like extracting meaning from these kind of contexts, if we give the context to the ChatGPT and ask the same question, it will say correctly iPhone 17 is powered by A17 Bionic chip. So this was launched like I think 2 or 3 weeks ago. Even then it has a good idea what it does. So, and this is not just limited to ChatGPT. So if you don't want to use a cloud solution at all, we can download the Meta AI's Llama model and do the same. So if we first ask it the same question, it will say iPhone 15 doesn't exist because this model also trained I think on early 2023 data. So it doesn't have any idea about iPhone 15 Pro. But for the same model, if we give the same prompt and the context and the question, it is now able to understand from the context. This has the iPhone 17 Pro. So using these kind of things, you guys might have seen there are projects like Chat with PDF, and there are other projects like AutoGPT. So all these projects behind the scenes use this technique to understand the similarity between all the data it can contain and extract all the meaning from it and give proper answers. So we also call this process as giving long-term memory to large language models. So yeah, that's all the things I have. If you guys have any questions, I can answer because it's kind of intimidating topic. But so this is what actually we did. If you want to give another summary, what we doing is when we have a question, before sending it to our language model, we can search a database and find relevant information about it and send that information along with the question to the large language model, because it's trained to understand large context and extract meaning from those things. We'll get more accurate results, and we can use this to extend the memory of large language models. So if you guys want to learn more about this topic, this Medium article is there, not Medium article, Keras example is there, which goes deeply into like how the this embedding calculation works and what it means. And if you want to learn more about transformers, I think this is a very good video you guys can watch. You can just Google this video.
Text data.
It's called Transformers Explained by Google Cloud Tech. So all in all, I think with this kind of knowledge we can build lot of cool systems, basically given by what chat with PDF has done. And I think that project got more than 2 million or something over a month. That the creator of that project is making good money right now because of this simple principle. So yeah, basically yeah, okay. So that's all I have. If you have any questions, you can ask. So I think our organizers has organized few gifts if you can answer 2 questions. So for now I will, so the two questions I have is, first one is, can anyone tell me what is the underlying architecture of ChatGPT? Underlying model architecture. What? No, LLM is what we call the language model, large language model. There's an underlying architecture I just talked about during the presentation. Transformative? Yes. Suresh? Yeah. And so the next question is, transformer architecture introduce few main techniques that set it apart from existing RNN based models. So can you guys tell me at least one of those innovations? Yeah. Okay, yeah, I hope I didn't bore you guys too much with this presentation, and if you guys have any other questions, you can reach me out in my socials. And yeah, thank you.
Thank you, Isela, for that session. To give the token of appreciation, I would like to invite Kushan Bharati. So the next session is on reinforcement learning, which is done by Mr. Ashank Priyadarshana, who is a tech lead at Cisco Labs.
මේක වැලුවේ තියෙනනේ. ඔක්කොම. පොඩි වීඩියෝ එකක් තියෙනවා. නෑ කමන්නේ මේ සවුන්ඩ් එක. මයික් එක.
මේක නියුස් කරන්නේ මේක
නෑ මේක යූස් කරන්න. I'm audible, right? Yeah, good afternoon. So I hope you guys are not hungry, so maybe you can just bear with me about 40 minutes, and I'm just here to talk about this rarely spoken area of machine learning or even AI, reinforcement learning. So at the end of the session, I hope so you guys will be interested in reinforcement learning, because it's bit rarely spoken or and I have mentored so many students, and I see I almost see none fourth year projects from reinforcement learning. So yeah, so this is me, as introduced. I'm a tech lead at Cisco Labs and graduate from Mora. I follow artificial intelligence masters also, and I have completed, I have done Google Summer of Code in 2017, that's way back, and some certificates, and I often write things also. Maybe if you go into this, maybe I have written how these neural networks learn in Sinhala actually. So how does this back propagation and gradient descent, those kind of things actually work in Sinhala, you can find in these Medium blogs. Yeah. So yeah, I'm representing Cisco Labs, so let me play you a video. Just observe it well, because there are some scenarios or operations that we currently practice with reinforcement learning. So we are trying to we are actually trying various things, and we are trying to innovate various things. With reinforcement learning, there are some operations that you would see in the video that currently we are trying out. At the end of the session, I will be asking, okay, what do you think? What would be the good operations that reinforcement learning in this video? Yeah. I hope sound is okay. Guys at the back, can you hear?
Since the dawn of time, we've foraged the earth for sustenance. But it was technology that separated us as a species. Technology that allowed us to eat better. Cultivate better. Design smarter ways to grow the food we wanted to eat. And perfected science to make it last longer. The ways that we choose to eat keep evolving. Food has now become an intimate part of our lives. It brings us together and shows how much we care, connects communities, and builds livelihoods for millions around the globe. But what if we could go further? What if we could trace the journey our food takes to better understand the impact it has on our planet? to make more sustainable food choices, transcend the limitations of time and space to create a future of boundless abundance, and push the technology that enables food service to its next frontier. What if we could better connect the world to share food and care for one another? At Cisco Labs, we're finding solutions to do just this, because the technology that moves food moves human civilization.
Yeah, so there are actually, I saw around 3 operations that if I am using reinforcement learning, that I could plug into those operations. Okay, let's move forward. Yeah, now, where is RL, which stands for reinforcement learning? So if you closely look at the slide, actually it's there, right, at the bottom. So I think that's all. I think I can go home, right? There it is, reinforcement learning. No, actually, why I put this is that we know in machine learning, there are mainly 3 branches, I would say, like unsupervised learning, supervised learning, and there is this reinforcement learning. So as I mentioned earlier, so I see many students, so even the industry, they are more focused on supervised learning and little bit of unsupervised learning, but rarely this reinforcement learning. But it's a very powerful technique that if you understood it very well, you would see even the world in a different manner. Yeah, so with reinforcement learning, we can do these things, and even one interesting thing is here that you see that with unsupervised learning and supervised learning, there are sub branches breaking apart, but with reinforcement learning, we don't see like that kind of a sub branching. So there's a reason for that, because as with Sri Lankan, even in the worldwide, it's a very developing field. There are no any standards to benchmark it. That's a problem, and so many researchers are going through under this one. Yeah, let's move forward. Okay, now again, we know that how do we learn in supervised learning? So we have data and we have set of labels. So what do we call learning in supervised learning? What we are trying to do is we maybe build up a model and we are trying to match the labels. We have a bunch of data and we know the answers. So we have in middle some kind of let's say artificial neurons. So we are feeding the data. So we are telling the model, okay, I am giving you a set of data, try to match it with these answers or these labels. So the model will, or the neurons will keep on updating. We use backpropagation or gradient descent for that. Yeah, for supervised learning we have data and labels. For unsupervised learning, we only have data. We don't have labels. With unsupervised learning, what kind of things that we do is we normally do clusterings, we do dimensional reduction, those kind of things. We have a bunch of data set, try to categorize these into set of clusters or set of classes. So those kind of things we can do with unsupervised learning. Now the interesting is with reinforcement learning, we can implement systems, or we can teach machines without data. So how do we do that? So that's an interesting philosophy, or interesting I would say pattern. We can train systems to learn something without data. So that's, I mean, you would ask from me, how do we do that? Actually that's based on experience. So that's more or less how we even learn, because we know when we are infants, we don't have lot of data, right? I mean, when we are starting to work, we don't even know how to speak. So that means our parents do not tell us, okay, okay, this is the way, you just move your left leg, and then after that move your right leg. So they don't teach us. Even though they tell us using normal language, we would not understand, because at that point of our life we don't understand language. But somehow we learn to walk. So how do we do that? So that means something is happening even with us. So with that philosophy, what we can do is we can train a machine or say a machine, okay, see, there are scenarios in the world, even without data, they are learning. So the philosophy behind is, even without data, we can learn by the experience. So that's the main philosophy behind reinforcement learning. We don't have data, but we can interact with the world. While interacting with the world, we can learn whether if I hit a wall, is that giving me a good reward? It's painful, right? I mean, that's a bad reward. So while interacting, I'll learn few things. So interesting thing is, with reinforcement learning techniques, we can implement those kind of techniques into machines. Yeah, again, so what is learning when it comes to, so I mentioned in supervised learning, learning is something like trying to match into labels or answers. Unsupervised learning, trying to cluster or categorize. Reinforcement learning is while interacting with the world, learning something. But if we come a level up, in general, when we say learning, actually what it is? So we can say learning is learning to take decisions. Given this set of data, into what kind of classification should I do it? Should I classify it as a car? Should I classify it as a bicycle? So that's kind of a decision taking, right? I mean, it has learned to take a decision. So in unsupervised learning, again same. It has learned to take a decision. Okay, should I categorize it into this set of data, or should I move this data point into this cluster? Again, a decision. So even with reinforcement learning, when we say learning, it's about taking a decision. So I said that, okay, it learns by experience or interacting with the world. So what it does is, even us, so in early years of our life, so we would see, let's say we saw a cat. So we saw a cat, so that means we take something into ourselves. We observe the environment, we observe the world. So that means we are taking in some states of the world, some observations of the world. Based on that observations, we have to do some actions. We don't kick it when we see a cat. I don't know, I don't do. So like that, we know, we take in a set of observations and choose an action to do. So that is learning. Perceive the environment, based on those perceived data or perceived state, what kind of actions can we do, and based on of those multiple of actions, what action should we do? That's the basic idea of learning, especially in reinforcement learning. But even if we think about it, even in supervised and unsupervised learning, learning is just given some data, taking a decision. Yeah. So now I talked about learning and what kind of reinforcement in reinforcement learning, what kind of things are we talking about. So in 2016, a special thing happened actually, especially in related to reinforcement learning. So this there's a game called Go. I don't know if you know about it. It's more complex than chess. So it says that the different combinations of it is greater than the number of atoms in the universe. It's not number of stars or number of galaxies or number of sands in the beach. It's number of atoms in the whole universe. So the different combinations of the game Go is even greater than the number of atoms in the universe. So that indicates the complexity of it. So it's a well populated, it's a well recognized or identified game, especially in China, even in Germany. So there are very masters of it. I mean, masters kind of people are there, level 1, level 2, level 3, like that. There are level 9, or I think level 9 may be the highest level in the Go championship. So in 2016, DeepMind developed a bot using reinforcement learning. So this bot initially, it did not know what are the rules of the Go. So it did not know what kind of action should I take. So it developed this, but in 2016 it defeated the highest Go champion in 2016. So it's an interesting, it's a five match game. 4 matches won by Go, 1 match I think draw. So interesting movie. It's available in YouTube. I invite all of you to watch it. I mean it's not a movie from the real life events of that match. They have constructed into a movie. So I think if you have time, we can look at the trailer of it.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to
Yeah,
get
so
underway.
he is the world champion.
Lee Sedol is
This
to
one,
Go
Lee
what Roger
Sedol.
Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the Deep Mind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there in fact a weakness?
The game kind of turned on its axis.
Well, look at this. That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I hate that something went wrong. Yeah, it's got it from a year ago.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So yeah, at one point of, at the 4th game, so he just walks away from the room. So he can't just take it anymore. Yeah.
It's
Yeah. So yeah, as I have stated here, if AI can master Go, what's next? It's a very complicated. It's a very, even the industry leaders could not believe it. There is a system or there is a AI that could master Go and defeat Lee Sedol. So yeah, that's a special turning point for reinforcement learning, and it showed the gravity or the capabilities of reinforcement learning. Okay. Yes. So what can be built with reinforcement learning? Yeah. At first, obviously, autonomous vehicles. Self-driving cars. We can develop, or they are being developed mainly using reinforcement learning, because at the end of the day, what a car or a self-driving car does is, so it just drives forward, observes the surrounding, based on the perceived background or the environment, it chooses action. Let's say a pedestrian or a human just jumped in front of it, it quickly observes it, and he has inbuilt set of actions, maybe a move forward, brake, turn left, turn right, reverse. Okay, let's say those are the 5 actions that he knows to perform on the environment. So he perceives the environment, sees a kid or a man jumps in front of the car. So with that information or the perceived set of observations, so he chooses the best action to perform. Hopefully he chooses to brake. Yeah, so we can develop self-driving cars, robots. Again, yes, when we are developing robots, so we need to develop them to master the environment, the normal world, right? So ideally, so we can't give him, we don't have training data for it. I mean, we are trying to build something very new, so it needs to learn by itself while interacting with the world. Look at the world, take some observations and choose the best action to do. Yeah, robots can be done. Then the recommendation systems. So obviously you should have experienced this one. I mean, the Facebook feed from one person to another is different, right? And even YouTube, TikTok, Instagram, even LinkedIn, all kind of social media, they are using this reinforcement learning for this recommending the next video, next post, next image, next dance, those kind of things. They are using reinforcement learning. For an example, what they would do is when you are signing into Facebook, let's say TikTok, so it does not have any idea about you. Maybe you are from Sri Lanka and your age is between this gap, so it does not know your interest, right? So it will just suggest various things, and based on your interactions, whether you did the heart action or liked it, just swept into his or her profile, based on those actions that you take, the agent behind the TikTok learns, okay, this guy at this point of time did this kind of an action for this kind of video. So it takes in that, okay, based on that actions or the observations that it took, he will suggest a next video. So that's kind of things we can do with reinforcement learning. Finance and trading, again, we can do based on the historical data, what kind of action should we do. So it's now you guys might think, okay, isn't it like a time series prediction? But no, time series is predicting, okay, next value, right? So now assume we need to build a kind of a bot based on the historical data or current observations. It needs to do some action, okay, buy or don't buy or sell. So those kind of actions, now there are 3 actions, right? So when we talk about reinforcement learning, we have to always think about, okay, what are the observations and what are the actions that we can do. So if it is a finance trading one, we see this, okay, the pattern is this, okay, what are the actions that I can do? Buy, sell, or just ignore. And even the game playing, of course, we know that NPCs are also being developed using reinforcement learning now, the non-playable characters and those kind of things. Yeah. Okay, this is the slide that I kind of a little bit complex in this whole session, but this contains the basic or the theories or the philosophy behind reinforcement learning. So if you need to understand well what reinforcement learning and talk about reinforcement learning, think about reinforcement learning, or can I use reinforcement learning for this kind of scenario? So if you understand this one well, I would say you are in a good starting position. Yeah, when we talk about reinforcement learning, there are about 6 major components. When you are talking about reinforcement learning, we are talking about an agent. Agent is a learnable kind of a robot or a system. And we have the environment which the agent interacts with, or the agent do some actions on top of the environment or to the environment. We have a reward. A reward means when he do some action, the environment will give him a reward. If I hit a kind of a wall, I'll be in pain. So that's a negative reward for me, like that. So we have reward. We have actions. I mentioned about actions a lot. Now, based on the perceived state or the observations, what kind of actions can we do? From those actions, what's the best action to do? That's the learning. Then we have a policy. Policy is kind of a strategy. While now if I want to build a robot to navigate through within this auditorium, so it needs a policy, right? Okay, in these places, if I move, if I try to keep moving past these chairs, it we can't do. So the policy would say, okay, you are in the presence of some set of obstacles or chairs, so choose a different action, you can't move forward. So policy is given this state, what kind of action should I do? So I can turn right or turn left. So the policy is basically what to do given these conditions. So given the states, what to do. There's a concept called value, but it's bit deep. So there is some mathematics involved in it, there's for interested persons, maybe you can look up this Bellman equation. So that's how we calculate the value. But for the simplicity of this talk, I did not include it. It's a bit complicated one, but the concept is very not that hard. I mean, idea is that we should not rely only on the reward. We should look past the reward also. Even though if I can maybe so maybe let's take a scenario like this. I'm going to sue. So it's a positive reward, right? I go to maybe a tiger cage. So I see a tiger for the first time in my life, and I see him up close. So that's a positive reward. So if I continue, okay, I'm getting good rewards when I go near to it. But after a certain point of time, if I go beyond that reward, go beyond that point, so then the tiger would take my arm or kill me. So we should not focus only on the reward. We should focus on the end goal also. After reward, what kind of things would happen to me? So those kind of things also we should take into consideration when developing it or calculating the policy. So that's basically the idea of value. So the process, there's the agent, it does an action. Based on that action, I mean action is done to the environment, on top of the environment. Based on that action, it would get some sort of a reward, a positive reward or a negative reward. And then with that, he will observe after he does that action, the environment would have changed, right? I mean, after if I move to this point, okay, now I see there's a path that I can move on. So after the certain action, I have to observe the new world, what has happened to the world. So that's the overall concept behind reinforcement learning. Now this table, so this table is kind of a policy for a recommendation system. So now let's see, the recommendation system is, let's say, TikTok. So now the TikTok agent or the bot tries to learn what are the good videos that I should show to this person. So let's say, as for the actions, as for the state, let's think that that bot takes in time. Okay, at which point of the time does this guy view this video or open the TikTok app? And then the now type, these are just arbitrary names that I mentioned here, the type of the video that he is currently watching. The third state is the action. Okay, what did he do to this video? Did he skip it? Did he enter into the profile, or did he continue on watching it? So those are the actions that TikTok agent would see. So here the agent is not us, the TikTok agent. So as the actions that it can perform is, what kind of video should I suggest him next, or after 2 or 3 videos later. So maybe a funny video, a sport video, a sad video, or kind of a dance video. So given so if we look at the first row, so at 10:09 a.m. so he is looking at a funny video and he does nothing, he just keeps on looking it. So then the agent sees this, okay, he is looking at a funny video at 10:09 a.m. And he does nothing. So for the next video, so agent would need to calculate, okay, what kind of video should I show him next. So maybe he can show him again a funny video, or a sport video, or a sad video, or kind of a dance video. So he needs to, learn this. What at 10:09, if he watch a funny video, what kind of video would he watch next to keep him in the TikTok application. So like this, now if you think of, so let's say, so from 10:09 to 11:15 he is hanging on the TikTok. So even there, so how many minutes are there, right? I mean the state space is very large. So this is one kind of a scenario set. So at 10:09 in another day he might be watching a sad video and he likes it. So at those point of times what he should what TikTok should show the human next. So these values you see, we call them Q values in reinforcement learning. So those are the learned things. Okay, for this section I am giving him so for the first row again showing a funny video, it has the highest value. So that means probably if he watched a funny video, next also I should show him a funny video. So that's the deciding criteria, so deciding ways that we can do. There are various ways. I mean there are things like so if we keep on showing funny videos continuously, so he might lose interest. So we have to do some sort of exploration. There is this concept called exploration versus exploitation. Exploitation is something like, okay, we know something and we keep on behaving according to the already knowable knowledge. But what if we want to do some experiments after a funny video? What if we show him a sad video? So that agent needs to learn that. All right, there may be some hidden interest of this guy after a sad maybe, or maybe we need to show him a dancing video. Okay, so that agent needs to learn about this, so needs to experiment on those things. So those kind of things also we can do with reinforcement learning, but I don't bring them here. I mean it's a bit of complex, but we can do those. When to explore, when to exploit, those kind of things we can do with reinforcement learning. Okay, yeah. Now I talk a bit about reinforcement learning and then a bit of theory and the philosophy, how to think in reinforcement learning concepts. So yeah, where does the deep learning fit in? Okay, so here I have drawn a small network for the previously shown TikTok recommendation system. There are various deep learning techniques that we can use in reinforcement learning. One is this DQN, and there is policy gradient methods. There are some actor critics methods. Don't be afraid of the names, they are just simple concepts. I mean the DQN networks we can use to guess the Q values. So what basically a neural network does is given the set of observations, so after observing some things from the environment, so it will try to guess the Q value. Okay, well, how good this action that you perform. That means so in the previous example, so he was looking at a sad video and the agent showed him a funny video after a sad video. So then the human might skip it quickly, so the reward will be negative. Okay, so this DQN, it would calculate, okay, that means he skipped very quickly, he does not like it, that means we should give him a very low Q value for that action. So value of that action is very less. Like that, there are policy gradient methods, networks that it tries to learn the policy. Policy means given this state what action should I take without thinking about Q values, calculating those kind of things. Basically it tries to learn given the states what to do. So that's the policy gradient thing. Then we have the actor critic methods. So they try to combine both of those things. I mean the Q value and this policy learning things. So yeah, we can build a neural network, and of course with Keras we can do it very quickly. It's just 4 or 5 lines. With Keras we can do it very quickly. So I'll show you at the end of this. I mean towards the end of this one. Yeah. So as the input parameters we take the observation. So the states, time, the type of the video that he is watching now, and the action that he took, whether he liked it, skipped it, peeked into the profile, those kind of things. Then we can have any number of hidden layers with any arbitrary number of neurons. At the end, as the output layer, so I'm showing here a actor critic network. As the output layer, we can have a softmax layer, which it will choose best action. So now remember, right? I mean when we are talking about reinforcement learning, we are trying to learn, okay, what is the best action that we can do, that we should do in this state. So at the end layer, the output layer, we need to have a softmax layer there. So then if we want to calculate the Q values also, we can get a single neuron and then get the Q value from it. So this is kind of a combination. I mean, this network outputs two things, right? There's a, as the output layer, there's a softmax layer and there's a normal neuron as well. So yeah, this thing we can build with Keras using only 5 or 6 lines. Yes. Yeah. Now yeah, let's go to gym. I mean, yeah, I haven't in a long time, but yeah, let's go. Yeah, so now as I mentioned earlier, I mean at the beginning of this session, there is this problem in reinforcement learning that it's not well standardized in the community or the industry. So this library developed by OpenAI, so it tries to standardize all of these things. So we know that when we talk about supervised learning or classification, we have this MNIST data set and ImageNet, those kind of things that we can play on and experiment on. For reinforcement learning, there was none up until GYM. So later it changed its name to Gymnasium. But yeah, so all of these images or the GIFs that I show here, all are already available in Gymnasium or GYM. They are just the environments. Now I'm talking about the environments here. So it provides a huge bunch of environments. So we can implement our various techniques or algorithms, even supervised or unsupervised, but mainly reinforcement learning techniques we can implement on top of it, and we can see how good it is. So various thinkings, right? I mean, you can think of various scenarios and implement those things on top of this. So like the top left one is a traffic control thing. So in a roundabout, all of these blue colored ones are agents or the reinforcement learnable agents. The green one is the one we are focusing on now. So given this scenario, what kind of actions does it do? So this is doable in reinforcement learning, and easily we can do it with Gymnasium library. So lot of research can have been done on top of it. Still they are being done. Okay, so it's not a solved thing. You guys can also do lot of research. So that's why I invite you to, when you are, maybe if you are undergraduates or even in the industry, think of doing research with reinforcement learning, because it's a growing field, and I believe after these LLMs, with LLMs, there's the next wave of artificial intelligence is with reinforcement learning, because this agent concept comes in this LangChain kind of frameworks as well, right? I mean, with LangChain we can build an agent and tell it to do these actions. So to do these actions, that action choosing part comes from reinforcement learning. With these reinforcement learning techniques, you can train a LLM agent to do various kind of things. Maybe after 2 or 3 years, you might see that, okay, we can develop an agent, tell that, okay, based on these observed things, go fetch some data from this API, or go fetch some data from this database. Okay, let's take a scenario. Okay, there are a bunch of APIs to get some data. What API should we choose? What action should we choose? Should we take data from an API or a database or some local files? Those kind of things we can model with reinforcement learning. So the age of reinforcement learning is actually after 2 or 3 years. I mean, once huge models been developed, I mean after ChatGPT, there's so 5, 6 kind of things. With those things, this agent concept would become prominent more, I mean, yeah. So as I mentioned, traffic controlling, trading, so there's an environment for training, trading environment. There are some Atari games kind of environments also where we can practice our algorithms, whether we have understood the concept, and then even the mobile network grid system. So when we know that when we are calling, or when we have a mobile device, when we move here and there, so we will get signals from various towers, right? Okay, how to, from which towers should we accept the signals? So that's built in our mobile phone. So those kind of things are already they are even with you now, although you don't know. So those kind of things we can experiment and we can do a lot of research. Yeah, the next part is now I am trying to teach a agent to drive up a mountain. So again, this is with gymnasium library. So here the goal is this car, it should learn to maybe go up a bit to that mountain and take some speed or the velocity, and with that velocity go up there and go to the flag position. So that's what now I am trying to teach, or actually I am not teaching. So this bot will try to learn. Yeah, let's see how we can do that with Keras. You guys are hungry, or just bear with me about maybe 5 or 6 minutes, that's all. Yeah. So this is the basic code. I mean, looks, there's about 27, I can reduce it to even 25 or 26 lines of code. This is the basic environment without any learnable thing or any neural network coded into it. So even with some comments, so if I run it, you would see that it does nothing, it just stays there. This is not training or learning anything, just doing some basic actions. So let's try to train it or tell it to learn itself how to do this. Let me close this. So yeah, let me explain the code first a bit, how we can build this kind of I mean the previously shown model kind of a deep neural network with Keras. So here I am using the functional API of Keras. So before that, let me explain the environment a bit about this one. So this is the gymnasium web page. So it explains all the things. I mean, these are the things that you can do. This is how you invoke or get a environment. So this one that I am trying to show you is okay. This one. So as you can see, so it gives a good description. Okay, these are the observations that you can observe from the environment. Observation in the sense is the first observation that it would get is the position of the car along the x-axis and the velocity of the car, what's the speed of the car. And as for the action space, it can accelerate to the left, in the sense it would decelerate. The action 1, how we encode do nothing is by the number 1. To accelerate right, we would encode it by the number 2. Yeah, so those are the observations. So 2 observations and 3 actions. Now see that there are 2 observations that we can do and 3 actions. So how we implement this in code is, see, so number of inputs is 2, number of actions that we can do is 3. So for the neural network input layer, so I am giving it as the 2 neurons. So 2 neurons should be there for the input layer. And for the action, so I am giving as num actions as the output layer. So that's the softmax layer. That's why I have encoded it as it should be a softmax layer. I suppose you guys know what the softmax layer is and what's the difference between a softmax and a regular layer. If not, please look at very simple concepts, right? I mean, even in my blog articles I have written in Sinhala what are these. And as the critic, that is the neuron which predicts or which gives the Q value. So that's it. I mean, how to build a model using Keras for this. So this here now we have, see, with this we have developed a model using Keras, just 5 lines, right? Just from 5 lines we have developed a neural network with 2 input layers, 1 hidden layer which consists of 128 artificial neurons, and 2 output layers. This may be something new for you guys. we can have more than one output layers. So here one output layer is this the action predicting output layer, which is a softmax one. The next one is a normal neuron. So with just 5 lines we can build a model using Keras, so it's very helpful. So then the rest is regular neural network building codes, like okay, what are the optimizers that we should use, what kind of loss function that we are talking about. So the rest of the code is not that complex, I mean not that different from a regular neural network building code. So yeah, if we run it, hope it's running. I mean, okay. Yeah, now it tries to learn what are the best things based on various actions that I should do. At the bottom of the hill, what kind of things should I do? Should I keep on accelerating? So it will not work. That's what you saw earlier. So it tried to keep on accelerating, but it did not work. So now it should learn by itself. I should go back and take up that velocity, and after that, while coming down the hill, I should keep on accelerating, maybe a little bit after that also. So after that, it will keep on learning based on various states by observing various conditions at this point of time. What kind of action should I do? Here the action is, should I accelerate, should I brake? That means I should I accelerate left side, I mean left in the sense that side, or should I do nothing? So yeah, so it will try to learn it, but it would take around 1 hour in this scenario. But there are a lot of researchers, I mean even for this one, how to implement a better RL model. So here what I have used is that actor critic neural network. Maybe using a DQN would be fine, or maybe using just a normal simple neural network which predicts the critic value would just do fine. But yeah, so I know kind of this is kind of a new thing. I mean maybe I have spoken very complicated words, or the words that you have never heard of. That's fine. I just by this session, what I want what I need from you is understand what is reinforcement learning. Just pick your interest on it. So just basically understand it. It's just how we learn it, right? I mean just like we are learning to ride a bicycle. Although we fall, we learn from those things and keep on learning how to ride a bicycle. That's it. The basic concept is that. But after that there are various technologies or algorithms, AI techniques that have developed by so many guys. Even this actor critic thing was developed very recently by a researcher. Is that it? Yeah. So again, I am from Cisco Labs. So we are building technology that moves human civilization. And as for references, these are the references. Yeah, so before you guys ask questions from me, I hope I can ask some questions from the audience, right? I can ask some questions from the audience, right? Yeah. So at the beginning, I played a video. I just want from your opinion, so based on the things that you learned now, with what kind of scenarios can we use reinforcement learning in supply chain in industry? So that means basically Cisco is a supply chain company, right? We are the largest food distributor in the world. We just distribute food. We buy food from vendors, we distribute them. That's the 1000 foot generalized version what we do. For that industry, for that we are building various kind of technologies. So let's take a warehouse. In a warehouse, in which point of for which operations can we use reinforcement learning? Maybe, there are valuable gifts. Anybody? There are no wrong answers. Okay. Exactly. Yeah, he gets it. At least I can be happy. At least one has learned what reinforcement learning is. Yeah. Can we have asked one? Yeah. Yeah. Exactly. Yeah, he gets it. Yeah, actually, those kind of things we are actually doing within the warehouse. I mean, we are trying to build various operations with reinforcement learning. I mean, although we have a bunch of data, how about if we try to build things with reinforcement learning, because it has proven its place in the AI, and as we know that it's the next wave of AI, so we are trying to build various things. One more? Yeah. Okay. Can you explain, I mean, what's the reward? What do we call a reward in reinforcement learning? Sorry? No, not in warehouse, just in general, what do we call a reward is? Okay, yeah, that's the idea. I mean, whether it's beneficial or not. Yeah, we can give him a present if there's more. Okay. Yeah, I think with that, my session ends. Yeah, so if you have any questions, or if you want some of these codes, you can reach me. These codes are available in GitHub, but I could not put it here. You can reach me, Facebook via our number, and then again, just think about using reinforcement learning in your projects, because it's an interesting field. Okay. All right. Thank you guys.
Thank you, Ashan, for that amazing session. So I'd like to call Suresh Piris to hand the token of appreciation. So the Keras Community has finally come to an end, and I'd like to take this opportunity to thank a few people who committed to this event. So first of all, I'd like to thank the speakers, Taraka, Keshan, Timira, Isala and Ashan for those incredible sessions that they conducted. Next, I'd like to thank the organizing committee who were very helpful throughout and made sure this event was a success. And finally, I'd like to thank all the participants who we had an overwhelming response with quite a few responses coming through. And you all were the lucky ones who had answered well and were selected to participate in the physical event. And of course, we have the online audience today as well. Thank you all for participating, and it's been an amazing day seeing such a big crowd here. So thank you very much for attending the Keras Community Day. Hope to see you all in the next event as well. Thank you very much. So finally, before we go, we want to take a photograph. Sorry, in front, right? So if all of you all can come to the front, we'll take a picture over here. Guys, we'll come to the front and take the picture from that side. So if you all can come to the front and face that side, that would make things easy.